Howdy, fellow calculus problem solvers. Today we're going to work out problem number 4 from the 2019 AB exam. And this is a combination of related rates and um, differential equations. So here we go. Number 4 says, a cylindrical barrel with a diameter of 2 feet collected rainwater as shown in the figure above. The water drains out through a valve not shown at the bottom of the barrel. The rate of change of the height of h of the water in the barrel with respect to time is modeled by a differential equation, which is dH dt equals negative 1/10 the square root of h, where h is measured in feet and t is measured in seconds. And they gave us the volume of a cylinder, which is pi r square h, but all of you guys knew that already. So it says the problem, find the rate of change of the volume of the water in the barrel with respect to time when the height of the water is 4 feet. So they gave us our Snapchat moment, and they want us to indicate the units of measure when we're done. Okay, so they gave us the HDT is equal to negative 1/10 square root of h. And we know that the volume of a cylinder is pi r squared h. And in our cylinder here, something's constant, which is really nice because we like that when it's constant, because then we don't have to find, with similar triangles or something, a relationship between r and h somewhere. So what's constant here the entire time the water is in this cylinder? Well, the r is constant, which is really, really nice. And it says the diameter is equal to 2 feet. So are they trying to trick us by giving this a diameter? Maybe, but we aren't going to fall for it because we know the radius is 1. Okay, so I can plug the 1, since this is constant, into my equation. I can say volume equals pi times 1 squared times h. And the only thing that's changing if the water is coming out of the barrel, since it's draining out, is h. So this is volume equals pi h. So when I take the derivative of this expression with respect to time, I get dv dt is equal to pi dh dt, because pi is a constant. And lucky for us, we happen to know what dh dt is. So I can say dv dt is equal to, let's hide this here, dv dt is equal to pi times negative 1 over 10 root h. And they gave me a Snapchat moment, right? What's a Snapchat moment? Well, they said that the water of the height is 4 feet. That's our Snapchat moment. And do I dare draw my little Snapchat guy here? I'm terrible at it, but there it is. There's my Snapchat moment. H is 4. So I'm going to go such that H equals 4 here. And we get dv dt is equal to pi times negative 1/10 times the square root of 4, which is 2. So the answer is going to be negative pi over 5, if I reduce in my head there. And this is going to be cubic feet per second, because this is a volumetric rate of change. And it's not asking how fast, which would be speed, which means we don't need the negative, but we do need the negative here. So our answer is dv dt is going to be negative pi cubic feet per second. Okay, we've indicated the rate of change in the units of measure. So there we go. That gives us 2 points. Yay. All right, part B. Part B says, when the height of the water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? Okay, well, they want to know if the rate of change is increasing or decreasing. So they want to know if my, dH/dt is increasing or decreasing. So how do I know that? Well, I need its rate of change, which is the second derivative. So this is going to be dH/dt, which we know to be, because they gave us, -1/10. I'm going to write this as the square root of h, but I'm going to rewrite it as -1/10 h to the 1/2. And then to take the second derivative here, we just need to use the power rule. But this is an implicitly defined function because h is a function of time, and we don't know what it is, so we have to use the chain rule with respect to time. So when I take the derivative of this, I get -1/20 h to the -1/2 times the derivative of the inside, which is dH/dt. Okay? And let's write that with the dH/dt in it. So this would be -1/20. I'm going to put the h to the -1/2 in the denominator. So this is -1/20 root h times -1/10 times the square root of h, which is just, this is a positive number because a negative times a negative is positive. So I get 1/200, it looks like, because the square root of h's cancel. And so the second derivative with respect to t of h is a positive number. And what would the units be? Well, if h is in feet per second, the second derivative is going to be in feet per second. Oops. Feet per second squared, which is an acceleration, right? And since this is greater than 0, what do we know about dH/dt? Well, then we know that dH/dt, we can say dH/dt is increasing since the second derivative with respect to t is greater than 0. Now, I should probably say at or when h is equal to 3. Okay, now, does it matter if h is 3 or 7 or 100 or... No, it doesn't, does it? Because the second derivative of h with respect to t is always constant. So that's pretty cool. All right. There we go. Part C, that's where the fun begins. But it's not difficult, okay? So part C. Part C states, at time t equals 0 seconds, the height of the water is 5 feet. So it sounds to me like they're giving us a point in time. So if I have a t and then h of t, they're giving me at time equals 0, 5 feet. Okay, that's my initial condition. All right, use separation of variables to find an expression for h in terms of t. So I'm going to take my differential equation, which is dH/dt, and that's equal to -1/10 times square root of h. And I'm going to separate the variable. So I'm going to get this to be dh over the square root of h, because I will have resisted and left the constant here on the right, and -1/10 dt. And then I'm going to rewrite this with an exponential form. So this is h to the -1/2 dh equals -1/10 dt. I'm going to pull out my magic integral marker. my magic integral marker. There it is. Okay, and when I do that, I get h to the 1/2 divided by 1/2, which would be 2, equals negative 1/10 times t plus c. All right, now I'm going to divide everything by 2. So this will be h to the 1/2, or the square root of h equals negative 1/20 times t plus c. And then to get the h all by itself, I'm going to square both sides, and I'm going to get h equals negative 1/20 t plus c, quantity squared. And now I'm going to use my initial condition. So I'm going to say using 0, 5, I can say 5 equals negative 1/20 times 0 plus c, quantity squared, which is really nice that this goes to 0, and I get 5 equals c squared. So c, in this case, is going to equal root 5. Now, it might be plus or minus root 5, but I think that root 5 is what we need, because if I go up here, it has to be root 5. It has to be positive up here. So then I'm going to put it back in my equation, say h of t is equal to negative 1/20 times t plus root 5. Oops, that root looks pretty. Plus root 5, quantity squared, is my equation for h. And we will have gotten a full 9 points on that free response. Okay, so the key things to know about this is on part A, you got to remember that it asked for units. So, this problem gives you a point for putting the units down. So that's a big deal. Okay, and in part B, it's worth 3 points, and you get a point for taking the derivative, the second derivative. Okay. And then you get a point for putting the first derivative in for dh dt, and then you get a point for this explanation. So it's important that you use your words to explain why the rate of change of h with respect to t is increasing. Now, the big point getter for this problem is part C, which is 4 points. Okay, you get 1 point for just separating the variables. So for this step alone, you get 1 point, which is pretty cool. Even if you didn't know how to integrate it, you would get 1 point. So separating the variables is important. You'd also get a point for taking the antiderivative. So you get a point for getting this and this correct for antiderivatives. You get a point for putting the plus c and using the initial condition. And then you get a point for your final solution. So there you have it, 2019 AB number 4, all worked out. So I'm going to move on to the next one.